Morning. Thank you, Yvonne, Carlos, for organizing this interesting event where everybody speaks with a chalk in one's hand. It's kind of a forgotten experience. So this is what I want to do today. I want to give you a bit of a broad brush idea of what we can do today about strongly interacting fermion problems, so the quantum many-body problem for fermions, mostly in the strong coupling regime, hence mostly with computational methods, which is a challenge to explain with a piece of chalk and a blackboard, but I'll try my best. And the way I want to organize that, so it's a very, very vast field, so obviously I can only give you some sort of broad brush survey focusing on a few things, and it's going to be fairly qualitative. The way I thought of organizing this is in sort of 4 steps. I want to tell you about physical platforms. By that I mean various forms of quantum matter that justify studying this field, and associated models. I will focus mostly on what I would call simple models. Simple doesn't mean that they are easy to solve. It means that they are simple in their formulation. Why do I do that? Because, of course, we would also like to have more realistic models of actual pieces of quantum materials. But this is really hard to explain on a blackboard in detail. And also, I only have 90 minutes. So I will mostly focus on simple models. Then I would like to tell you a bit about what kind of physical questions we want to ask. And of course, you are also welcome to ask questions. Then I will tell you in very qualitative terms about methods, mostly computational ones. Here, I will try to convey the notion that a computational method doesn't mean blindly simulating a piece of stuff on a computer, but is always rooted in a concept, and that the concept itself on which a given computational algorithm is built is a way to look at nature, to look at physics, and provide specific insights into the problem you're looking at. And then I will, of course, show you a few results or highlights on these models and questions. So that's the menu. Let's see if I get to this. OK, so first, the sort of platforms and associated models. So I will briefly talk about 3 kinds of 3 forms of quantum matter. The first one, you could have guessed, given the sort of general tone of this meeting, is going to be ultra-cold atom in optical lattices. So that's the first one. Then I will say a few words about what I would call classic forms of quantum matter and correlated materials. Classic is not in the sense of classical, but in the sense of time-honored, things that have been studied for decades. And lastly, I will say a few words about much more recently emerging forms of quantum matter, especially moiré materials. OK, so these are the 3 things I would like to briefly talk about, again, in very, very qualitative terms. So first of all, so that would be 1, 2, 3, 4. And let me first talk a bit about cold atoms. Okay, so everybody in the room, I guess, knows that one can cool down atomic gases down to very low temperatures, let's say in the nanokelvin range. And I guess everybody also knows that it is possible to trap these atoms into periodic potentials created by lasers. So in one dimension, this would look like this. This is, of course, a theorist view of what's going on in the lab, right? So we would have two counter-propagating laser beams that create a periodic potential. And the atoms have an induced dipolar moment. They are neutral atoms, but they have an induced dipolar moment due to the field of the laser, and they hence will interact with the laser potential. And depending on the type of atom and the conditions, blah, 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 the atoms may want to be localized either at the minima or the maxima of this potential, hence realizing a sort of egg box-shaped potential, if we do this in 2 dimensions, in which you can think of the atoms as billiard balls being located, let's say, at the minima of the potential. So I would have my atom somewhere here. But of course, being quantum particles, they can hop around, traverse these barriers by the tunnel effect. Another way to say this is that the individual wave function of two such atoms overlap, and this overlaps around particle transfer from one well to the other, right? They not only hop around, but they also interact. So, as you know, if we have two atoms and they collide, there is a scattering length, and this is going to generate an interaction energy for putting two atoms in the same well. So if I now want to add another atom here, I'm going to generate an on-site energy, which is traditionally called U, which is going to be something like the spatial overlap of the interaction strength, which in this context can often be approximated as a delta function with a Vanier function, which is this single particle wave function located here, centered at site I square, and the same Vanier function centered on the same site because I'm considering the interaction on the same lattice site. Okay, so you see that at the end of the day, because this potential is local, this is really something just like this. I've used translation invariance of the Vanier functions, very roughly speaking. And of course, G can be controlled because it is proportional to the scattering length, and to some extent, we can control scattering length even in the presence of the lattice by the so-called Feshbach resonances. So we have control on G. At least the experimentalists have control on G. And I've pronounced one important word here, which is control. These platforms are highly tunable and controllable, and the tools at the disposal of the experimentalist to control these systems are the strength of the interaction, which can be tuned with Feshbach resonance, which means ultimately magnetic fields, or the amplitude of this periodic potential, which can be tuned even more easily by just changing the power of the lasers. So the strength of the power of the lasers will control the depth of this optical lattice. I can have a very shallow lattice or a very deep lattice. And hence, this will control the spatial extent of these Vanier functions, which also enter this expression. So you see that this interaction strength is tunable in two ways, both by controlling the power of the lasers and, in principle, by controlling the Feshbach resonance, if you can do that in the presence of the lattice. Similarly, the hopping amplitude, which I talked about a little bit earlier, which is the ability of the atoms to hop from one well to the other by the tunnel effect, hence the amplitude being called T, like tunnel, is going to be something like the integral of the kinetic energy taken between two Vanier functions located at site Ri and Rj. And that would be Tij between two lattice wells. So this guy here can also be tuned, mostly by changing the extent of the Vanier function and hence the power of the lasers. Okay, so these are the two very basic elements that are the dominant terms in the effective Hamiltonian of the system, provided, of course, that we can limit ourselves to only one type of Vanier function here, which means that when you solve for, say, the band structure of the non-interacting particle problem in this periodic potential, all the bands are well separated. So if we have, I'm going to make a classic plot that you've all learned about in textbook solid-state physics. This is my k² over 2m. Right now I have a periodic potential which defines a certain Brillouin zone. I'm making all my drawing in one dimension because I'm not so good at drawing in more than one dimension, right? This is going to fold the bands like this, and so on and so forth. We're going to open gaps by Bragg scattering at the edge of the zone, and this is going to define bands, tight binding bands, something like this, and so on and so forth, right? So when this separation, let's call it delta, between bands is large enough, it is enough to focus on just, say, one band. I can construct the associated Vanier function associated to the block wave of this band, which is the W that enters these equations, and I'm home. Of course, as the lattice is made shallower and shallower by reducing the power of the lasers, I may have to worry about other bands coming into the picture. And here I've been a little bit perverse because I made a drawing in one dimension. In one dimension, bands really do not cross. But in more than one dimension, bands can cross. There are all sorts of topological properties associated with these band crossings, by the way. And hence, you really have to worry about whether that separation is big enough or not. Okay? But for the rest of the talk, I will mostly assume that these bands do not cross, and we can focus on a single effective band. Okay, in that case, what is the effective Hamiltonian? Well, let's imagine we have atoms which live in two possible states. These states would be typically hyperfine states of my atoms. Let me call these states up and down. Up and down is evocative of spin, but really in this context, it is the hyperfine states of the system. So let me consider fermionic or bosonic particles with two possible hyperfine states. Then the effective Hamiltonian that comes from this on my lattice, keeping only one band, which will be something like this, minus T, sum over, say, pairs of nearest neighbors of and sum over the two hyperfine states of C dagger I sigma C j sigma. So I guess everybody is familiar with this notation. C dagger creates fermions with spin or hyperfine state sigma on site I, and C destroys it, plus the opposite process, because particles can hop from right to left or left to right. And then I would have here a term plus U, sum over I of Ni up, Ni down. Here I have assumed that the particles are two-component fermions, and hence on a given site I can only have four possible states, 0, up, down, or up, down, because of the Pauli principle, right? If I had bosons, I could have many more particles on the same site, and hence this term would be just, if you want, something like U over 2, sum over I of Ni, the whole thing square, which you can think of as some sort of charging energy if you want an electrostatic analogy to this problem, right? Okay. So this model is a very well-known, iconic model for the whole field of strongly correlated quantum matter. And I'm sure you all know about it. It's called the Hubbard model. It is a very, very simple model to formulate. It's controlled by only one coupling constant, which is the ratio of U and T, dimensionless. This U is an energy, T is an energy. U over T is a dimensionless number, which controls the coupling strength in this problem. It's very simple to write down, but it's actually a very complex model to actually solve or even understand. Let's not even talk about exact solutions. Okay, so in doing so, I want to emphasize that I have made a sequence of approximations. I have killed all other bands. I've assumed also, in fact, that the range of interactions does not exceed certain bounds. If these conditions are violated, and this is something which is often dismissed in discussions of this field, but I want to just emphasize it to not talk about it in the following. If, for example, you have a more shallow potential, you would have to include other bands in this description. There are also conditions on the scattering length for this to be true. And when such conditions are violated, you may need to add extra terms to this Hamiltonian. And in fact, these extra terms may even be interesting. I want to point out one extra term, which is something we emphasize with Felix Werner in maybe one of his first papers ever, which is a density-assisted hopping term which has been recently revived in interesting studies of superconductivity by Steve White in particular, which is a term like this. It's a term that hops particles from one side to the other, but conditions to the existence of another particle on one of the two sides with the opposite spin state. So it's a four-body term, which you can think of as a density-assisted hopping process. And actually, this term may be interesting in its own right and could be, I guess, the subject of studies in the field of cold atoms. Another simplifying assumption I've made is that this hopping term here is purely nearest neighbor. And in the context of cold atoms in optical lattices, this is actually a very, very good approximation. And in fact, in many contexts, it's actually even difficult to induce a next nearest neighbor hopping amplitude. The reason is easy to understand. comment est-ce qu'on l'efface ici? Ah, voilà. It is because very often, in this context, the periodic potential that you generate is separable in space, which means that it is, let's imagine we are in 3 dimensions, we have a potential V of x, y, z, and it's actually the sum of separable potentials along each direction. If we place our laser beams at 90 degrees one from the others, right, we have just the superposition of three separable potentials. And as a result, the Vanier functions are also separable. They are products of x, y, z. And then by very easy symmetry arguments, you will realize that if we are, for example, in a 2-dimensional lattice, so I wouldn't have that term here, the hopping along the diagonal of the lattice would be 0 in these circumstances. So I want to emphasize this term, and it's traditionally called T prime. That will be hopping along the diagonals, because it is often not there or very, very small, and I'm speaking under the control of experts in the room, in the context of cold atoms in optical lattices, but it is actually a very important term to induce some of the phenomenology we like in the 2-dimensional fermionic Hubbard model, in particular, as you will see if I ever get there, supraconductivity. Okay. So I want just to end this very elliptic introduction to this form of quantum matter by a remark about energy scales. So what are the energy scales we are talking about? And maybe I would have to erase something here. I guess this. No, because I want to keep cold atoms there. So the typical value of the hopping amplitude in this context, give or take an order of magnitude, okay, is that the hopping amplitude in the lattice would be typically in the kilohertz range. And if you convert kilohertz into energies, this means something like 100 nano-K. So this is a typical order of magnitude for the hopping amplitude. And as I emphasized before, U over T, the dimensionless coupling constant, can be tuned. And it can be tuned very widely, let's say from the weak coupling regime of order 1 to the very strong coupling of order 20. Okay? But of course, you just have to be careful in experiments, because if you're going to have U over T to be too large, then your particles are not going to move very easily, and the thermalization times or the equilibration times may be very, very long. On the other hand, if U over T is very small, this may mean that you've increased T somewhat. And if you've increased T too much, you may have to worry about other bands. Okay, so this being said, there is a wide range of tunable U over T in which you can still do experiments. But I want to mention that this energy scale, the things I really want to emphasize is that this energy scale, which is, of course, in absolute terms extremely low, is actually incredibly lower than corresponding energy scales that we're going to see in the next chapter when it comes to the solid-state form of quantum matter. In the solid-state form of quantum matter, at least in the traditional correlated quantum materials, the hopping amplitude is a fraction of an electron volt, right? Maybe 1/3 of an electron volt, say in cuprate superconductors. So an electron volt, as you probably all know, which is not an energy scale comparable to this at all, is actually 11,600 Kelvin, right? So you see that between this scale and this scale, there are many, many, many orders of magnitude, right? So if we want to compare the physics of cold atomic systems to the physics of solid state, we just have to remember that we are talking about the same phenomena, but over energy scales that have absolutely nothing to do one with the other. And this is a testimony to the beauty of physics, that we can actually address the same problems with completely different platforms. Now, the last energy scale I didn't talk about is temperature, which is very important. And here is the catch, that actually cooling these ultra-cold, so-called ultra-cold fermionic atomic systems has been a real challenge and is still a very ongoing challenge. I'm optimistic, and I guess we're all optimistic, that the field is going to advance towards cooler and cooler stuff. But the ratio, the key ratio, is the ratio of T over T. Or this is a bit of a theorist notation. I should put a Boltzmann constant here, kBT over T, right? So this ratio is something like, in the best experiments currently, of the order of 0.2. And this is even perhaps a tiny bit optimistic, but there are experts in the room who can comment on that. A few years ago, it was more routinely 0.5. And 10 years ago, it was basically of order 1. So convert this to the condensed matter context, you see that 0.1 even, okay, would be in the 1,000 and more Kelvin range, right? So in fact, whether you want to call it ultra-cold quantum matter or whether you want to call it ultra-hot quantum matter is actually a matter of opinion. And this is not aimed at putting down the field. In fact, there are some very interesting phenomena in the high temperature regime that are poorly understood. I will come back to this later a little bit if I have time. At this rhythm, maybe not. Especially transport in this temperature regime where kBT over T is of order 1 or slightly lower is poorly understood. We have very few methods to actually address this problem theoretically, analytically, or computationally. And this is a wonderful platform to actually address this question, because if you try to address this question, at least in traditional solid-state physics, either the solid melts, which is not what you want, or it vibrates like crazy, and you have phonons that intervene in the problem, while here the lattice is fixed. Okay? Good. So this is all I wanted to tell you about cold atoms in optical lattices as a possible quantum platform. So now I have to press on what? Yes. I got it. And I now want to come to my second example, which is, let's say, traditional strongly correlated materials in the solid-state context. Okay, so traditional solid-state, traditional strongly correlated matter in the solid-state context started perhaps a century ago when people realized that the standard bond theory of solids could not explain that certain materials were insulating when standard bond theory would actually predict them to be metallic. And perhaps one of the first examples, if not the first one about this, was nickel oxide, which is a partially filled band and nonetheless an insulator. And I think it is MOT, and others who in the late 30s pointed out, of the previous century, pointed out that this is due to strong interactions. Okay, so since then the field has developed enormously. There are thousands of examples of materials which display strong electronic correlations, many of them in the field of transition metal oxides, or TMOs. The reason being that the d orbitals of a transition metal are rather well localized around the nucleus, and so you retrieve this notion of well localized Wannier functions, and hence that the overlap between these orbitals from one atomic site to another is relatively weak as compared to the on-site value of the screen Coulomb interaction U. And here I've already said a word which is kind of worrying. You see that in the cold atom context, you know quite precisely what U is. You can also measure it in various spectroscopy experiments. While in the context of solid-state physics, it would be extremely naive to estimate U from just taking matrix elements of the bare Coulomb interaction. That would give values of order 20, 30 electron volts, much, much too large to be realistic. And the key phenomenon that reduces this value of U is screening, the fact that in a metal, if you put a test charge at long distance, the Coulomb potential is screened out and decays faster than 1/r, typically exponentially. And as a result, the strength of the effective Coulomb interaction seen by a given d band in an oxide, let's say, is more on the scale of a few electron volts. So it's reduced by basically an order of magnitude. And because the bandwidth are typically also of the order of a few electron volt, the ratio U over T can be of order 1 or 5 or something like this. Hence, they fight each other, and we are in the interesting regimes where electrons are not completely localized and are also not completely itinerant, which is the interesting regime where strong correlations are manifest. But the price to pay is that the actual value of U is not known so precisely. It requires complicated full first principle calculations of the screening phenomenon to be able to say, to estimate, let's say, the value of this parameter. Okay, so that's a traditional platform for strongly correlated materials. Another one is, I'm not going to talk about it, but I just mentioned it for the record, is rare earth atoms, which have even more localized atomic orbitals, the so-called 4f or 5f or actinides orbitals, which are very, very localized and hence lead to very, very narrow, almost atomic-like bands. And then there is a third traditional platform, which is often a little underestimated but very interesting, which are organic-based crystals. And I'm going to say a few words about this. Okay, so all this field has existed for basically a century, but it's been put back under the limelight now almost 50 years ago when the famous copper oxide superconductors were discovered by Bednorz and Müller in 1986. These materials, so high-TC cuprate superconductors, these materials are oxides of copper. This is an iconic example. So it contains a copper atom, which has a partially filled D shell. It contains oxygen, so it's an oxide of copper. And importantly, it contains a third element, which brings controllability to the system. So I'm not going to say too much about this, but it's important to know that basically the crystal structure of these materials are made of copper, which is inside an octahedra of oxygen. So this is in the plane, and there would be two so-called apical oxygens far away here and here. But the thing which is important to understand is that the materials are very anisotropic. They are very quasi-two-dimensional because this distance here from this oxygen to the plane is much larger than the distance there, right? So the materials form essentially planes of copper oxygen, which have this structure. Now I'm looking from here. I have copper atoms, and I have oxygen atoms on the links in between. And most of the physics of the system can be understood from thinking mostly about the physics in these two-dimensional copper-oxygen two planes. Now, you could ask, well, but why does that have anything to do with sort of a simple model like the Hubbard model that I described before? Because obviously, even though I've simplified tremendously the problem to just one copper-oxygen plane, this plane contains many atoms, hence many orbitals. Each copper atom, the active shell, is the 3D shell of the copper atom, hence it has 5 d orbitals plus spin, which is 10 quantum states. 5 because L is equal to 2, and 2L plus 1 is hence 5. Okay? And the oxygens have at least a partially filled 2p shell, hence it has at least 2 orbitals in the plane, px or py, and py, which are relevant to the problem. Okay, the trick is that, yes, copper d shell has 5 orbitals, but the filling of copper is nominally 3d 9. So it contains 9 electrons in the d shell. And because of the crystal structure of the system, which is this very distorted so-called perovskite structure with a c-axis much bigger than a b-plane, the 5 d orbitals that are actually degenerate in the atom get split by the crystal field into a bunch of orbitals here. It's not exactly like this, but this is just a cartoon. And we have to place 9 electrons into this. And you see that this means that we're going to have one orbital that contains a lone electron. All the other ones are filled. When 2 electrons leave deep below Fermi level into a single atomic state, these electrons are pretty much inactive. So at least if you are a ball theorist, you can just decide to forget about all these guys, and you are left with 1 electron in one orbital, or if you want, a half-filled band. This band is actually not originating from the direct hopping from copper to copper, because you see that there is an oxygen in between. So what actually happens is that the topmost orbital here, which happens to be the so-called dx squared minus y squared orbital, which has a shape like this. I'm not drawing the sign of the lobes, but it's x squared minus y squared. Hybridizes with the px and py orbitals of the oxygen. This overlap allows electron to hop. So the hopping is through oxygen, right? And this is how you realize basically a single band system, which is half filled in this pristine compound here. And an on-site interaction, which is actually due to the fact that if you need to hop from here to here, you have to pay a price which is the nominal energy difference between the atomic level position of the D state and of the P state of oxygen. So U, in this context, if you really want to reduce this to a single band model, is not the on-site Coulomb interaction on copper, but it is much more related to the energy difference, the so-called charge transfer energy, between copper and oxygen. So it is a long-standing debate in the field whether it is legitimate to reduce this problem to a single-band Hubbard model. Obviously, from the drawing on the board, it looks a little bit more reasonable to keep both copper and oxygen orbitals to describe, which will then bring 1, 2, 3 bands in the problem, to write a generalized form of the Hubbard model that would contain a U on the copper, charge transfer energy, a hopping TPD between copper and oxygen. This is the so-called 3-band model, often called the Henri model. To start from this, study that model, and perhaps reduce it in some regimes to the single-band Hubbard model. OK, so I'm not going to elaborate further on the electronic structure of cuprate superconductors, but I want to tell you a little bit about phenomenology, which will also start bringing some of the questions I have put here on my list of, on my menu. So what do these cuprate superconductors do that surprise us? So here I'm going to draw a phase diagram which has temperature on the vertical axis and something on the horizontal axis called doping. I will call it delta. It could be called, well, let me call it X for the purpose of this talk. And this is so-called doping. So what does it mean? Well, I say this structure is controllable to some extent, and this is because I forgot, or I purposely did not yet talk to you about the third atom. The third atom is lying something in between these planes, right? And chemists know how to make chemical substitution on that site. They can replace lanthanum by strontium, for example, leading to an alloy, something like lanthanum 2 minus X, strontium X, copper O4. And lanthanum is an atom that wants to be 3+. It wants to lose 3 electrons, whilst because it has such valence. And strontium is an atom that wants to be 2+. Hence, to maintain charge neutrality of this structure, when I do this, I have to remove electrons from the copper-oxygen plane. This is called hole doping. So here I'm putting hole doping, which in practice means inserting, for example, strontium. In this system, we could do other things like oxygen vacancies and so on. And then very interesting things happen, which you've all heard about, I guess. First of all, when the system has no doping, this material is one of these Mott insulators, which is an insulator despite the fact that it has a half-filled shell. And it's actually an insulator which at low enough temperature becomes ordered. So there is an ordered antiferromagnetic phase here, an antiferromagnetic Mott, or actually more properly designed charge transfer insulator. Charge transfer because U is really the charge transfer energy. And this Néel temperature here can be high. It's typically several hundred Kelvin, let's say 400 Kelvin. Upon doping, this antiferromagnetically ordered Mott insulator very quickly loses antiferromagnetism. So this would be the antiferromagnetic phase, typically up to only a few %. And what happens is what gave the Nobel Prize to Bednarz and Müller in 1987, which is here we form a superconductor with exceptionally high Tc for the time, which can reach, let's say, almost 200K. So high Tc superconductor. But then there are many other interesting phenomena in this system. One of the interesting phenomena is that if I now look at the metallic state here, because with open insulator, it becomes a superconductor. This state is a metallic state. By metallic state, I mean that if we measure resistivity in this state, resistivity versus temperature is going to be increasing with temperature, right? 0 dT positive. The more we heat up the system, the more resistive it is. That is kind of a definition of metallic behavior. Here, the system behaves in a very bizarre manner, which is called strange metal, which of course doesn't say much, just means that it is unusual. And why is this metal strange? Because in this region, and only in this region, well, maybe I should be a little bit more generous. There is an extended region like that. In this region, the resistivity of the system, this would be Tc, where it falls to 0, is actually incredibly linear up to over a very large temperature range. So resistivity is going to look like this. And this is quite an unusual phenomenon because at least if we explore the very low temperature regime of metals dominated by electron-electron interaction, if we go to low enough temperature such that phonons are no longer active, we expect the resistivity of a more conventional metal to behave like a constant because there are impurities at low T, plus a T square temperature dependence. The T square temperature dependence is because two particles, two fermions that want to collide are strongly limited in their phase space. And if you apply some simple Fermi golden rule argument, you will realize that this limits phase space considerably so that the collision rate has to behave like T square. This is an argument that was put forward by Landau and gave rise to the so-called Landau Fermi liquid theory. And so you see that the strange metal regime of the copper oxide superconductor is a challenge to Landau Fermi liquid theory. Now, this behavior of perfect linearity does not persist down to the arbitrarily low doping. If you actually measure resistivity in this regime coming down that way, what you will find is that at high temperature, the resistivity is still linear, but then before it reaches Tc, it does something like that. So it deviates from linearity. And in fact, if you look at the physics of this metallic regime with other probes, you discover something which is surprising also, which is the following. If you measure the magnetic susceptibility of this metal versus temperature, instead of finding a constant, so another defining properties of Fermi gases and Fermi liquid is that the magnetic susceptibility is constant at low temperature, right? This is Pauli susceptibility, right? Well, in this regime, that's not what is seen. What is seen is that the resistivity is sort of, the susceptibility is sort of constant at high T, but below a certain temperature that we call T star, it goes down. So susceptibility in, let's say, free fermions is related to the density of states of the system, right? So if you interpret this phenomenologically very simply, this means that you are sort of losing density of states. So you are losing the ability to excite the system. The density of excitations becomes lower than what it should be. It is not the behavior of a gap. In a gap system, you would expect if there is a spin gap, the susceptibility would fall to 0, right? But it doesn't quite fall to 0. It sort of diminishes upon cooling. And this is why people call this a pseudo gap. And this phenomenon was discovered back in the day in 1989 by several researchers, in particular our colleague Henri here at the University of Orsay. And this was discovered indeed by a magnetic probe, namely NMR. So this is a regime which has a pseudo gap, which is also something we want to explain. Now, there are additional complicated phenomena in this system, which I barely have the space to draw on this diagram. But here, there is a regime in which charge density wave appears. So the local charge density is modulated in space. And here, there is a regime of somewhat more normal metal. Not quite, but more conventional, let's say. This regime is called the overdoped regime. This is called the optimally doped regime. And this is called the underdoped regime. OK, so you see already some of the questions that we want to address, which are, well, first and foremost, can we understand that the system is actually a high TC superconductor? And is that physics contained in the simplest-minded single-band Hubbard model with repulsive interactions, which a priori may not seem so favorable for superconductivity? But even perhaps equally intriguing is the behavior of the so-called normal state, which is not so normal, namely the pseudogap phenomenon. What causes that? Who ordered this? And the strange metallic behavior. And of course, this is a phase transition, the red line here. This is a phase transition. But although this is sometimes debated, this is a crossover, which is this T star pseudogap line, is a crossover. There are some indications from neutron experiments that there may be some accompanying phase transition at T star from our colleagues, Philippe Bourges, for example, and co-workers. But this may not be actually the driving mechanism of the pseudogap. This may be a phase transition, at least that's my personal opinion, let's say, that rides on the opening of the pseudogap. And this is definitely a crossover. So this also brings me to something which is conceptually very important in this field, which is that the physics of strongly correlated quantum matter is not only about ground states and phase transitions, but it is also about understanding crossovers, which, whether we like it or not, play a very important role in the phenomenology of these systems. So, you know, the whole edifice of theoretical physics has been built on the notion that we should actually start by understanding the ground state. We should then understand elementary excitations around this ground state. And then that the high temperature regime is associated either with a phase transition in which we lose the order which is present in the ground state, or with some appearance of incoherence of some sort at high temperature. But basically, the established edifice, let's say, of theoretical quantum condensed matter physics is that we have a ground state. We need to understand the ground state wave function and, very importantly, the low energy excitations. And that these low energy excitations remain coherent up to a rather high coherent state, coherent temperature. So here we have well-defined quasi-particles a la Landau. And at some point, this gas of quasi-particles become unstable to some instability, and that would be the broken symmetry. So we would have an ordered state here with a quantum critical point between one type of ground state and another type of ground state. But you see, the notion is that you form quasi-particles first. They are very coherent in the normal state. This gas of quasi-particles has instabilities. And if we understand the elementary excitations here in the disordered state, which lead to the notion of quasi-particles, how this gas becomes unstable, and the nature of the ordered state, we've understood everything. Okay, so this is the standard model, the standard, not model, this is the standard conceptual framework. But you see that this standard conceptual framework is actually challenged by these sort of things, because here, for example, it is not at all clear we are forming coherent quasi-particles before anything interesting happens. So this is why we may need to think differently. Okay. So very briefly, I want to tell you a little bit about organic crystals. And I will erase this here. I'm, of course, running very late. So I'm not going to try to write the name of the molecules because I would not be able to do that. They are sort of flattish-like big organic molecules that you can actually assemble into a crystal. And typically, in those systems, which are called the BDT salts, these crystals form also planes, and these planes are actually triangular. So something like this. And these materials, perhaps in contrast to the cuprates, are very well described by a one-dimensional Hubbard model, a two-dimensional Hubbard model on the triangular lattice. Or more precisely, actually, to be really accurate, they are anisotropic triangular lattices. So it's better to think of a square lattice in which you put a T prime only on one diagonal. So you have T here and T prime here. And these materials here are typically half-field bands, half-field single-band systems. They can be doped, but this is delicate. There are some examples of successful doping. And their phase diagram is mostly studied as a function of temperature and pressure because they are very soft plastics, so pressure is a very good tool to study them. The undoped material display the following phenomenology. So pressure brings the molecule closer to one another, hence the bandwidth larger. And what happens is that there is an insulating state, again, a multi-insulating state at low pressure. There is a metallic state at high pressure. In between, there is a first-order phase transition, like a liquid-gas transition that separates the two. This scale is about 40 Kelvin. And when you cool down the metal, it becomes a superconductor with a transition temperature, which is actually quite high as compared to the bandwidth, 14 Kelvin. So this is also a high TC in relative terms, superconductor. And here there is, again, an antiferromagnet insulator. But in contrast to the cuprates, at least over a very large range of pressure here, these systems are Fermi liquids. So there is a Fermi liquid coherence scale below which coherent quasi-particles do form, and the resistivity is T squared. So here it's a Fermi liquid. There may be a very tiny region here near the metal-insulator transition with some hints of a pseudogap like this, but this is very narrow range. Okay, so since I don't want to devote all the lectures only to platforms, and this was supposed to be only the first part of my talk, I will very briefly tell you about a new development in the field. Or maybe I should bring this up. How do I do this? Okay. And I want to tell you about the last type of platforms that have recently emerged in the field, and these are moiré systems. I forgot to say here that the typical hopping integral, if you want to map this onto a Hubbard model, is going to be more like a third of an electron volt. Okay? The other thing I want to say here is that I don't want to leave you under the impression that most correlated quantum materials of this type, transition metal oxides of rare earth systems, are well described by the one-band Hubbard model. In fact, the one-band Hubbard model is an exception. There are very, very few materials that are described even reasonably by the one-band Hubbard model. As I explained here, this is a very specific instance of copper. This is due to the fact, and there are very few other materials that do that. There are some, iridates, for example, but most other transition metal oxides absolutely require that you introduce additional bands, additional degrees of freedom in the system because of the other d orbitals. So I want to emphasize that very strongly.
May I ask just a very quick
Yes.
So in comparing the two, of course, the d orbitals are important here. Mostly here is p-like orbitals.
They are complicated molecular orbitals, yes.
So is the superconductivity also
Unconventional? No. So
like
here superconductivity is proven to be D-wave. Here it's not entirely clear what it is, but D-wave is also a strong candidate. It's definitely not local as well.
Okay, so it's not local.
Yeah. Okay, so obviously you've all heard about this. The last platform I want to mention are moiré materials. And this is, I would say, to a certain extent, a byproduct of all the beautiful graphene physics that has been developed over the last 2 decades. And this is, roughly speaking, what is going on. As you know, one can actually synthesize in the lab very beautiful 2D crystals. These crystals could be, of course, graphene, which would be a honeycomb lattice, as you all know, but there could also be what is called transition metal dichalcogenides, typical example being, for example, tungsten, selenium-2, just took about one, but there are hundreds of them. These systems form 2-dimensional crystals, and you can actually stack these 2-dimensional crystals on top of one another. So you would have a plane of, say, WSE2 and a plane of another material, let's say molybdenite, for example. And both of these materials are 2D crystals, but they have different lattice spacing, or you could also take the same material, and what physicists and chemists can do is actually rotate slightly one plane with respect to one another with a controlled angle. So this is called the twist angle, in which the main axis of this plane and this plane are rotated by a certain angle theta. And this creates a superlattice, which you can see by taking 2 graphene sheets and put on transparencies and rotating one slightly with respect to another. which creates a much bigger unit cell and an interferometric pattern that looks like a moiré pattern. This moiré pattern is, for example, typically in this case, a triangular lattice of moiré patterns. And the corresponding electronic bandwidth of this superlattice is very, very small and controllable by the twist angle. So the actual devices look something like this. Here they would put some HBN, for example, hexagonal boron nitride, and some gates, some electrostatic gates. And these systems become very controllable platforms in which you can control the bandwidth, the electronic structure, and to some extent, the strength of the interaction by acting either on the twist angle or on the electrostatic potential of the top of bottom gates. A whole range of very interesting phenomena has been found into these materials. The most spectacular one being in 2018, so you see this is very recent, the discovery of superconductivity again by Pablo Herrero and co-workers at MIT in twisted bilayer graphene. And very recently, actually a few months ago, the discovery of superconductivity for the first time in bilayers of TMDC, both by the Columbia group of Corridine and by the Cornell group of Kinfei, Mack, and Jeshan. So these are very, very actively studied materials. They lead to very narrow bands. This is the theoretical proposal of Bistritza and MacDonald, which suggested by tuning the twist angle, you can engineer very, very narrow band systems. And when I'm talking about very narrow bands, I'm actually talking about hopping amplitudes, which can be on the milli-electron volt scale. So bandwidth here at, say, the magic angle, well, there is, say, T, can be a few MeV. So you see, this is 3 orders of magnitude smaller, or 2 orders of magnitude smaller than what you have in the transition metal oxides. So that actually U over T is, again, tunable, but say in the range of 5 to 10 maybe. And interestingly, this brings some of the aspects of ultra-cold atom physics into condensed matter, because now we can actually have temperatures which are sort of a fraction of T or comparable to T. 1 milli-electron volt is 10 Kelvin, as you probably know. And hence, a bandwidth of, say, 10 milli-electron volt is 100 Kelvin. So we are back into a regime of rather high temperature if we want to. But of course, we can also cool down the system down to millikelvin and study them at millikelvin temperatures. So I'm not going to elaborate on this. This leads to all sorts of interesting physics and interplays between correlation and topology, for example. And it's a very, very active field. OK, so now I realize I have something like 20 minutes for the rest of my talk, but it doesn't matter. We'll manage something. What do I have to do? This one doesn't work, so I'm going to do what?
No, you put 1 or 2. Up 1.
OK. How do I? There is monté, but there is no descent. OK. By elimination, I declare this must be descent. OK. And yeah, 1 cannot be moved. OK, good. OK. So I promised you that I would talk about questions. Well, I've already talked about questions, right? Why is this material superconducting, pseudo-gap, strange metals, and so on and so forth? Did I forget some of the questions? Yes. Well, to some extent, I did talk about transport. I also emphasized that, although I didn't show examples, that understanding transport at very high temperature is also a question. Anyway, I think I've talked enough about some of the open questions. So now I want to tell you a little bit about methods. And this is going to be an attempt to review 40 years of computational work on quantum many-body systems in 10 minutes. But I'll try. OK, so the regimes in which we want to understand these systems are mostly strongly interacting regimes, which means that what we can do with pen and paper is actually very limited. There are some phenomena we can rationalize either a priori or a posteriori with some calculations inspired from weak coupling theories. We can gain a lot of insight from the opposite limit, which would be a completely isolated atom or strong coupling if you want. But we can't go very far with purely analytical methods. So one has to resort to computational methods. If you read the Nobel lecture of Phil Anderson, he even says one has to resort to the indignity of computational methods. But what I will try to convince you of is that computational methods are actually rooted in deep conceptual ideas, A, and B, that they have allowed to push the field from a state where essentially nothing was understood 30 years ago to a state where now we can understand a lot of things and answer many of these questions. So I will leave the indignity to where it belongs. OK, so I want to review briefly computational methods. Although I have to say, to the credit of Phil Anderson, is that he changed his mind in the later stage of his life about these methods. Computational methods, together with organizing principles behind these computational methods. OK, so it is actually very useful to think in the following way. This would be a plane that has temperature, and this would be coupling. And you can organize the various available computational methods in this plane by saying that there are methods that focus on zero temperature, first and foremost, so which are addressing here the ground state. And then, with some luck, try to make their way to describing excitations and hence perhaps finite energy or finite temperature properties above the ground state. There are other methods that actually start from the opposite point of view, high temperature, where every correlation length for any incipient order is very small, and then physics is very local. So there are methods here that exploit the principle of locality. I will go back to this. And then there is a third class of methods that attempt to start from weak coupling and try their luck at exploring sufficiently the perturbative series in weak coupling to make their way to strong coupling. So there are methods that proceed in this way. OK, so let me try to review some of these things in at least simple qualitative terms. So the methods that deal first and foremost with ground state face the following problem. If we think of the big many-body wave function of a quantum interacting system, this is a function, if I look at it on some computational basis, let's say, for example, I have a spin chain, right? Just a Heisenberg spin chain, just two fixed ideas. I can use as a basis state the quantum number Sz on each site, which I will denote sigma 1, sigma 2, sigma 3, each one of these being 0 or 1 or plus or minus h bar over 2. So the wave function of this guy is going to be a sum over sigma 1, sigma n of an amplitude psi naught of sigma 1, sigma n times my basis state. And this, to be modern, I should talk about qubits. Okay, we have n qubits. And the size of the Hilbert space is 2 to the n. Now, if you are a computational person, first question you're going to ask is, can I store this on my computer? So imagine you gather all disk space available on the planet, absolutely all of it, and you try to store this on this massive hard disk built of all disk space on the planet, and ask yourself, up to which value of n can I do that? And the answer is, well, the total number of storage in the planet is not completely well known. I asked ChatGPT, and it gave me an uncertainty of basically 2 orders of magnitude. But roughly speaking, it is known up to a factor of 100. And when you do a very simple little math, you will see that what you can do is store the wave function of 80 spins. OK. So this is far from 10 to the 23, right? So there is absolutely no way you're going to be able to store this wave function for any reasonable system except for small molecules. So what do you have to do? What you have to do is compress. And so all these methods here are legitimately obsessed by the compression of information, which, by the way, is very useful stuff for many other applications. So how do we do this? Well, the breakthrough in this field came in 1992 by Steve White, who proposed a way to compress this wave function. In fact, he did not exactly. What he did really is propose an algorithm to optimize some compressed wave function, and then later on, it was realized by himself and others that the underlying construction was a specific type of compression called matrix product states. And the idea behind a matrix product state is that instead of, we're going to make an ansatz for this amplitude, which is the following. We're going to write this amplitude as a product of matrices, which will be of times m by m. We need two matrices, one for upspin and one for downspins. And we're going to do products. So this is going to be M1, M2, M2, M3, and so on. I'm going to be sloppy about boundaries, if you don't mind, because this is a qualitative lectures. Something like this. The last may be a vector and not a matrix. Same for the first one, actually. Let's say there is an M0 here. So M2, M3, M1. Yeah, it depends. I can do trace or not. It doesn't matter. Something like this. But it's a product of matrices. And the size of these matrices is limited to dimension m. So instead of having an exponentially large number of degrees of freedom, I have a number of degrees of freedom that scales like n times m squared times perhaps 2 for a spin chain. Okay? And the idea is that by increasing the size of these matrices, you can eventually obtain a better and better representation of the wave function. This can actually be proven in particular cases. And the concept behind this is that the matrix product state representation is a good representation when the entanglement entropy of the system is not of my state is not too large. So the entanglement entropy is something that measures how connected are or how independent the wave function between two parts of a subsystem is. So imagine my system is in a state, a pure state psi for the whole system psi AB. Right? I construct the density matrix rho AB, which is psi AB, psi AB. And now I construct the reduced density matrix rho A, which is the trace over B of rho AB. And I look at how the entropy associated with this density matrix, which is minus rho A trace log rho A, trace, okay, behaves. And the statement is that in systems in which, if I split my system, let's say like this, into A and B, the entanglement entropy of the subsystem B grows not like the volume of B, but like the area around B, this representation becomes extremely efficient. So you see that these computational methods that store the wave function in MPS form are rooted in a concept, which is the concept of low entanglement, which makes the compression work when the entanglement is low enough. It does not work all the time. And furthermore, one can use a very efficient algorithm to optimize the energy of this variational wave function. You can think of this as a variational ansatz. This algorithm is called DMRG, density matrix normalization group. And it basically amounts to optimize these matrices one after the other, sweeping the system in one direction and then in the other direction, and using singular value decompositions of these matrices at each step to minimize the energy. So really the success of this method is rooted in the idea of low entanglement and works for systems that have low entanglement, which is true especially in 1D or quasi-1D system. And is two things. First of all, a clever variational ansatz and a clever variational algorithm to optimize these wave functions. Okay, so this is one example. Much more recently, there is another class of compression that appeared, which is applications of neural networks. And this is now called neural quantum states. I obviously don't have time to describe that. I was planning to say a few words about this. But the basic idea is to encode this not as an MPS, but as neural networks in which the entry layers are my n qubits, and the hidden layers here, for example, are connected to this by various connections. The optimizing parameters, the variational parameters being, for example, weights here, biases on these bits, biases on those bits, and the connection between those. So this was started in particular by a paper 7 years ago by Carleo and Troyer. Okay, so these are ground state methods. Now let me tell you a few things about those methods here. So those methods are based on the notion of locality, and they exploit the fact that the correlation length can be small in some regime. And when I say correlation length, it could be the correlation length of any incipient order in the system. So this will happen at high temperature, but it will also happen at large doping or far from phase transitions. In that case, we have our system, and it's very reasonable to think that we can replace our system by an equivalent local system. So we're going to consider a small local system into a big system, hence the term which is now used for these methods, which are called quantum embedding, because you embed a small system into a larger system. And the poster child of these methods is dynamical mean field theory, which was also introduced in 1992. It was quite a glorious year for these sort of methods. And dynamical mean field theory, or quantum embedding methods, in contrast to wave function-based methods, are based on Green's functions. So it's based on an object which is called the Green's function between two sites and say 2 times. And it makes an assumption on a basic building block of this object, which is called the self-energy. The simplest approximation being that the self-energy is going to be assumed to be purely local in this approximation in registry with this idea of locality. Given this assumption, you can rigorously map the system onto one small quantum system in an effective bath, which is a very familiar idea for mean field theory, except this is a generalization of mean field theory to quantum many-body system and to, if you want, an effective Weiss field which depends on energy or time instead of being just a number. Okay, so this approach has been very successful to describe this regime where physics is reasonably local. And especially one of the big advantages of this approach is that it can be combined with electronic structure methods to actually describe real solids, real materials, which are not limited to single-band Hubbard models. Furthermore, a bit in the same way than these MPS methods can be systematically controlled by increasing the size of the matrix M, which is called the bond dimension. This type of method can also be systematically controlled by extending the construction not only to one site in an effective medium, but to a larger cluster of sites in an effective medium. Obviously, if your cluster was as large as the lattice, this would be an exact solution. And hence, if you can converge this method in the size of these objects, you also converge to the exact solution. Okay, so the problem, you see, is that these two types of methods work according to very different organizing principles, locality versus entanglement. And more importantly, they use as their basic object very different objects. This uses a humongous object, which is the full wave function of the system, this uses a much more compact object, which is the Green's function or the density matrix and things like that. And so for many years, the dialogue between these two types of methods was basically impossible for two reasons, because it was addressing different range of parameters, and it was also handling very different objects. A big advance in the field that has happened in the past 10 years, roughly, is that now those methods can talk to one another. And the reason is that the MPS DMRG-based methods are now able to go to somewhat finite temperatures. And the progress in quantum embedding methods have allowed to go down in energy and temperature to range where the physics is significantly non-local. And so they can start talking to one another. And actually, when this happens, it's like having the fog dissipating on a landscape. You start seeing the global picture. OK, so now I didn't talk about the third kind of method, which is very, very important and in full development, which is trying to access the strong coupling regime from weak coupling. And obviously, can I take 15 more minutes?
15 more?
Yes, I think I need 15 more minutes. Otherwise, it's going to be boring. You want the answers. 12. Give me 12.
OK, I give you 10.
OK, 10. Fine. Good negotiation. So last category of method I want to mention is diagrammatic Monte Carlo. So diagrammatic Monte Carlo aims at the following idea. If you take any observable in the system, let's say some thermodynamic quantity Q, you can expand it in power series of U. Right? And typically, for Feynman diagram aficionados, the Qn is going to be represented as a sum of Feynman diagrams. The idea behind diagrammatic Monte Carlo is actually to sample, instead of calculating painfully all these diagrams one by one, which of course the number grows like crazy at large orders, you're going to sample those diagrams by Monte Carlo sampling methods. And this idea was started by Prokofiev and Fistunov in 1988. So you see the mid-90s were really prolific for all this stuff. The challenge being, once you've been able to determine by sampling this Qn with enough precision, can you go to large enough order? Question one. And even more importantly, can you resum this series? OK, so here, usually, somebody raises in the audience and says, this cannot work because we know the Dyson argument that at 0 temperature, negative U would have a superconducting instability, and hence the radius of convergence of this series must be 0. Well, this is not true because we are working at finite temperature. So at finite temperature, the radius of convergence of this series is actually finite. And so we can hope to be able to resum this series at least up to this radius of convergence. Usually, however, the radius of convergence is not as large as what we would like. And so there are all sorts of mathematical tricks to actually try to change variables. So we apply some transformation U prime equal f of U to actually push this radius of convergence to large enough values. Now, the progress in this field has been to realize that if you do not insist in summing only connected diagrams, you can represent the Qn's as a determinant. I'm talking about fermions now. And furthermore, that you can actually use recursion relations to go from the disconnected diagrams to the connected diagrams by systematic recursion relations. And this led to the so-called connected determinant algorithm, which is due largely to Riccardo Rossi when he was working with Felix and Chris for his PhD. And has been since then developed a lot by many people, including Fedor Simkovich, Michel Ferraro, many others, and Felix and Chris, and has led to a lot of progress in the field, at least at intermediate temperature. So to give you an idea, the current ability of this method for fermion is addressing U over T's maybe to about 6 and reaching temperatures T over T, which is something, if I want to be a little optimistic, like this, and still improving. Okay. So there are, of course, many other sampling methods that I have not covered, many other variational wave functions that I have not covered. But since I have only 5 minutes left, what I want to do is to tell you a few important results that have been established by these various things. Okay. So I'm going to start by ground state. So now in a few minutes, I'll just give you a summary, a sort of status report of what we understand about the 2D Hubbard model by a combination of all these techniques. And I'm focusing on 2D fermionic Hubbard, just for lack of time. Ground state. So what we know for the ground state, of course, at half filling, when the density is 1 per site, or delta is 0, doping delta, the ground state has antiferromagnetic Lagrange order. At T equals 0. Of course, at finite temperature, this spin Lagrange order is killed by the Mermin-Wagner theorem and fluctuations. And this is why, by the way, it's also very important to understand crossovers, because in 2 dimensions, ordered states resulting from the breaking of continuous symmetry cannot resist finite temperature, and everything becomes crossovers. Now, what happens when we dope? So when we dope, it's been now essentially established by all methods that if there is no T prime, I remind you T prime is the next nearest neighbor hopping, the ground state at low doping, so this would be U over T and doping, the ground state at low doping has both charge order and spin order in a pattern which is called stripes. So what is this? This is a modulation. So now I'm going to make a plot in which the factor -1 to the I of the antiferromagnetic ordered, which is staggered between the A and B sublattice, has been removed. And on top of this very fast modulation odd even, there is an envelope which is a spin density wave, right? So that would be the modulation of the spin density wave. And I'm going to draw on this picture the charge density wave that happens. And what really happens is that the holes like to be at the nodes of this charge density wave. So the electron density is going to do something like this. And you see that the modulation of the charge is half, the wavelength is half the modulation of the spin. That is the standard spin pattern, stripe pattern. I'm not telling you that this is always the case here, but this is sort of a cartoon. So all methods agree that stripes is a very favorable ground state at low doping. The really tough question is whether this wins over, say, superconductivity or not. And this question has been, for most of this phase diagram, answered by highly accurate combinations of DMRG and another method, which is called auxiliary field quantum Monte Carlo, with the answer that at least for most of this phase diagram, when T prime is 0, stripes actually win. The tricky thing is that the difference in energy between a stripe state and a superconducting state are very, very small. They are of the order of 1% of the hopping. So this requires very accurate numerics. Now, does that mean that the Hubbard model does not sustain superconductivity in the ground state? Well, the answer is no. When T prime is different from 0, it has been recently established in the past couple of years that in that case, this energy balance here becomes favorable to D-wave superconductivity, which eventually wins over stripe ordering. The ground state can sustain both charge density wave and superconductivity together, but there is a non-zero D-wave order parameter. This is to a certain extent work in progress, so I don't think it is currently possible to draw a full complete phase diagram, but at least it has established that indeed superconductivity exists in the ground state in the presence of T prime, which is something we knew for many years that T prime was a good thing for superconductivity. This was established by quantum embedding methods many years ago, but the delicate balance between stripe and superconductivity is a recent development. Okay, so I will finish by telling you what we understand about the pseudo gap, and then I will stop.
Is that for the discussion session?
Let me just summarize what we know about the pseudo gap. Yeah. 1 minute.
It will be too short.
Pseudo gap. It will be just 2 sentences. Okay. So a combination of quantum embedding DMFT methods and more recently finite temperature extensions of DMRG MPS methods have established that the pseudo gap is actually associated to short-range antiferromagnetic order at strong coupling. So we can keep this for the discussion session where I can explain this more in detail, but in weak coupling, we have a well-established theory, analytical theory of the pseudogap phenomenon, which is due to Wilk and Tremblay, again from the mid-90s. And Nicolas Dupuy contributed also to this back in the day. This Wilk and Tremblay theory is actually telling you that long-range antiferromagnetic fluctuations in 2D can create a pseudogap, provided that the correlation length for antiferromagnetic order is larger than the Dobrev wavelength. I can explain in the discussion session how this theory works. But this is a weak coupling theory, and the point is that in the regime where pseudogap is actually observed, this antiferromagnetic correlation length does not satisfy this criterion. So we have a puzzle. Now at strong coupling, what both quantum embedding methods first, then diagrammatic Monte Carlo methods, then also finite temperature extensions of DMRG have established is that a pseudogap can appear even in the regime where psi is small. And psi is small, meaning psi over A of the order of 2 to 3 lattice spacing. So it doesn't need to satisfy this criterion. And the picture of the system, if you want, is small bubbles of antiferromagnet, or perhaps even just singlets, with holes moving in between. And this quantum fluid has a pseudogap. So this is now seen by basically all computational methods. It started with quantum embedding and DMFT, but it's now very well established. Okay, well, that's it.